GPT-4 cost over $100 million to train. Not to build, not to deploy, just to train. And most of that money went to one single company, NVIDIA. But here's what nobody tells you. Training a large language model isn't just one thing. It's actually 5 completely different stages, each with its own costs, its own challenges, and its own breakthroughs. So today I'm going to break down exactly what happens at each stage, where the money actually goes, and why some companies spend millions while others train models for pennies. Stage 1. Data collection and pre-processing. Before any training happens, you need data. A lot of data. We're talking about trillions of words scraped from the internet. The most common source is something called Common Crawl. It's a nonprofit that crawls the entire web and makes the data publicly available. But raw web data is messy, really messy. You've got duplicate pages, spam, malware, adult content, personally identifiable information. So the first step is cleaning. And this is where things get interesting. Companies use something called deduplication. This removes exact copies and near duplicates at massive scale. Why does this matter? Because if the model sees the same Wikipedia article 100 times, it'll memorize it instead of learning patterns. That's called overfitting. Next comes quality filtering. Not all web pages are equally useful. A scientific paper is more valuable than a random comment thread. So teams train small classifier models to score each document. Anything below a threshold gets thrown out. Then there's toxic content filtering. You don't want your model learning from hate speech, violence, or illegal content. This requires another classifier pass plus manual review for edge cases. Now, let's talk about the scale here. GPT-4 was reportedly trained on around 13 trillion tokens. What's a token? It's roughly 3 to 4 of a word. So 13 trillion tokens is about 10 trillion words. That's roughly 10 million average-length books. But not all data is free for high-quality sources. Like academic papers, books, and proprietary code, companies sign licensing deals worth millions. The total cost for data collection and pre-processing? Anywhere from $1 million to $10 million. Mostly spent on data licensing, human curation, and compute for cleaning pipelines. Stage 2. Pre-training. This is the big one. This is where 70 to 80% of the total cost goes. And it's deceptively simple in concept. The model's only job is to predict the next word. Give it the sky is and it should predict blue. That's it. That's the entire training objective. But to do this well, the model has to understand everything. Grammar, facts, reasoning, common sense, writing styles, all emerge from just predicting the next token. Now here's where the cost explodes. To make this work at scale, you need compute. A lot of it. The biggest models use clusters of 10,000 or more GPUs. Not just any GPUs, NVIDIA H100s, which cost around $30,000 each. So that cluster alone is worth $300 million in hardware. Now let's talk about the math behind training cost. There's a formula that researchers use. Flops equals 6 times n times d, where n is the number of parameters, and d is the number of training tokens. Flop stands for floating point operations. It's a measure of how much computation is needed. For GPT-4 with roughly 1.8 trillion parameters, trained on 13 trillion tokens, we're looking at around 1.4 times 10 to the 26th flops. That's a number with 26 zeros. An H100 GPU can do about 2,000 trillion flops per second under ideal conditions. But in practice, with multi-GPU communication overhead, you only get about 40 to 50% utilization. This means training GPT-4 took roughly 3 to 4 months of continuous compute. Now let's break down where the pre-training money actually goes. Compute rental or ownership is 70 to 80% of cost. For GPT-4, that's roughly $70 to $80 million. Electricity is another 10 to 15%. These GPU clusters consume megawatts of power around the clock. That's 10 to 15 million just in electricity bills. Infrastructure and cooling is 5 to 10%. GPUs generate enormous heat. You need specialized cooling systems. Data centers with liquid cooling, redundant power, network infrastructure. Finally, engineering salaries eat up another 5% or so. You need world-class ML engineers who can debug training runs at 3 a.m. Because if a training run crashes midway through, weeks of compute and millions of dollars could be wasted. This is why checkpointing is so critical. Teams save model snapshots every few hours so they can resume if something fails. Stage 3. Supervised fine-tuning or SFT. At this point, we have a model that's great at predicting the next word, but it's not great at following instructions. If you ask it a question, it might continue the text instead of answering. It's essentially a completion engine, not an assistant. So we need to teach it what helpful responses look like. This is where human annotators come in. Companies hire hundreds or thousands of contractors. Their job? Write high-quality instruction response pairs. Things like, explain quantum computing to a 5-year-old, followed by a clear, accurate, well-written response. The key insight here is quality over quantity. You don't need billions of examples like pre-training, just 10,000 to 100,000 really high-quality ones. Each one is carefully reviewed and revised. Studies have shown that a small amount of diverse, high-quality data can dramatically improve a model's instruction following ability. The term for this is the alignment tax. It means there's a trade-off. The model might become slightly worse at raw next word prediction, but much better at being actually useful to humans. Cost-wise, SFT is relatively cheap compared to pre-training. We're talking $100,000 to $1 million. Most of that goes to human annotator wages. The actual compute for fine-tuning is minimal since the data set is small. Stage 4, reinforcement learning from human feedback. RLHF. This is where the magic happens, and honestly, it's kind of wild. SFT teaches the model what a good response looks like, but RLHF teaches it to prefer better responses over worse ones. Here's how it works in 3 steps. Step 1, collect human preferences. You give the model a prompt and generate 2 or more responses. Then a human annotator ranks them. Which one is better? Is response A more helpful, more accurate, less harmful? This creates a data set of preferences. Step 2, train a reward model. This is a separate neural network that learns to predict human preferences. Given a response, it outputs a score. How much would a human like this? The reward model is trained on all those ranking data points. Step 3, reinforcement learning. Now we use the reward model to fine-tune the main model. The algorithm is called PPO, Proximal Policy Optimization. Basically, the model generates responses, gets scored by the reward model, and then updates its weights to generate higher scoring responses. This loop runs thousands or millions of times. The model learns to avoid toxic content, stay on topic, be helpful, all without explicitly being programmed to do so. Now there's a newer alternative called Direct Preference Optimization, DPO. It skips the reward model entirely and trains directly on preference data. It's simpler and often works just as well. This is what many open source models use now. Cost for RLHF? About $1 to $10 million. Roughly $500K to $2 million for collecting human preference data. $100K to $500K for training the reward model. And $500K to $5 million for the actual RL training runs. RL is notoriously unstable. You often need many attempts to get it right. Stage 5, Inference Optimization. The model is trained, but now you need to actually serve it. And here's a critical insight most people miss. Over time, inference cost will exceed training costs. You train once, but you serve millions of requests per day forever. So companies invest heavily in making inference faster and cheaper. Technique 1, quantization. Model weights are normally stored as 16-bit floating point numbers. Quantization converts them to 8-bit or even 4-bit integers. The model uses half or quarter the memory and runs faster, with minimal quality loss, maybe 1 to 2% worse. Technique 2, distillation. You train a smaller student model to mimic a larger teacher model. The student learns from the teacher's outputs, not the original data. You end up with a model that's 10x smaller but nearly as capable. Technique 3, KV cache optimization. When generating text, models need to remember previous tokens. This uses something called a key value cache. Optimizing this cache can make generation 2 to 3 times faster. Technique 4, speculative decoding. A small fast model drafts several tokens at once. Then the big model verifies them in a single pass. If most guesses are correct, you generate much faster. Cost for inference optimization work, about $100K to $1 million. But the ongoing savings can be tens of millions per year. So let's put this all together with a cost comparison. GPT-3 with 175 billion parameters cost around $4 to $5 million to train. GPT-4 with roughly 1.8 trillion parameters cost $50 to $100 million. LLaMA 270B, Meta's open model, cost around $2 to $5 million. Claude 3 Opus, estimated at $50 to $100 million. Gemini Ultra, Google's flagship, likely over $100 million. But here's the interesting trend. Efficiency is improving dramatically. LLaMA 3, despite being more capable than GPT-4 in many benchmarks, likely cost far less to train thanks to better techniques. Open source models are closing the gap fast. Mistral, Qwen, DeepSeek are training frontier-class models at a fraction of the cost. Now let's talk about inference pricing. GPT-4 Turbo charges around $10 to $30 per million tokens. Claude 3 Opus is $15 to $75 per million tokens. GPT 3.5 is dirt cheap at 50 cents to $1.50 per million. Open source models via APIs like Together or Fireworks, even cheaper. Or you can run them locally for just electricity cost. So let's recap the 5 stages. Data collection, $1 to $10 million. Pre-training, $10 to $100 million. This is the bottleneck. Supervised fine-tuning, $100K to $1 million. RLHF, $1 to $10 million. Inference optimization, $100K to $1 million upfront, massive ongoing savings. Total for a frontier model, $20 to $130 million. But here's the wild part. These costs are dropping fast. Better hardware, better algorithms, better data curation. What costs $100 million today might cost $10 million in 2 years. And when training costs drop, more players enter the game. More competition means more innovation. That's the flywheel that's making AI progress so fast. If you found this breakdown useful, consider subscribing. I break down complex AI topics like this every week. Thanks for watching.